All right, hello everyone, and welcome back to Hypothesis Testing Video Lecture Series. Today we are going to be testing hypotheses about a population proportion. So in the last two sections we have been testing claims about the population mean. Starting today we are going to be testing claims about the population proportion or percentage of a population. So when you're doing a hypothesis test about proportions, these are going to be claims such as, the proportion of the state population that is in favor of a bill, or the proportion of people who carry a specific gene, or the percentage of people who believe in aliens, something like that. So testing for a proportion is going to involve a binomial distribution where you have two outcomes, success and failure. P is the probability of success and Q is the probability of failure. Now, you might remember from chapter 6, hold on, why can't I underline? There we go. Give me a minute. Should have done this earlier. So P is the proportion of success and Q is the probability of failure. Now, P hat, you probably recognize this back from chapter 6. P hat is the proportion of successes in a sample. So P hat is the sample proportion of successes. And if the sample size times probability of success is greater than or equal to 5, and sample size times the probability of failure is greater than or equal to 5, that means the proportion of successes in the sample is going to be approximately normal. Because of this, you are going to use the standard normal distribution whenever you are testing a claim about the population proportion. So for proportions, for a hypothesis test for a proportion, you are going to be using z-scores again, and you are going to be using the standard normal distribution. Because as long as these two conditions here check out, P hat is going to be normally distributed. So these are going to be claims that test, these are going to be tests that about a claim about a population proportion P using the test stat P hat. So we are going to be testing claims about a population proportion P using the sample proportion P hat as our test stat. So this is going to be a z-test. So the z-test for population proportion P is a statistical test for a population proportion. Now you can only use the z-test when n times P is greater than or equal to 5, and n times Q is also greater than or equal to 5. That will guarantee a normal distribution. The test statistic that you are going to use is the sample proportion of successes P hat. So this z-score formula is going to be very different than the ones we used for mean. Because obviously the one that we used for mean, involved mean. This doesn't involve mean at all. This uses proportion. So the z-scores here are going to be P hat, the sample proportion, minus P, the hypothesized population proportion, divided by the standard error, which is the square root of PQ over N. So when you're doing this on a calculator, I would recommend putting parentheses around the numerator and parentheses around that entire fraction inside the square root. So this is the process in words to use a z-test for a population proportion. Population proportions always involve z-scores and a z-test. You're not going to have a test about a population proportion involve a t-distribution. We're going to be using z's. So this is a z-test. First, you need to verify that you can use the z-test in the first place by checking these two conditions. So check that n times P and n times Q are both greater than or equal to 5. Then you're going to state your two hypotheses. You're going to translate your claim into math, figure out whether that's the null hypothesis or the alternate hypothesis, and then whichever one you got, get the other one. You should have both hypotheses by the end of step 2. Then you're going to specify the level of significance. And the easiest process to use for this is rejection regions. So we're going to determine the critical values that go with our rejection regions. Now remember, you need to identify whether this is a left tail test, a right tail test, or a two-tail test. So you're going to use the inverse standard normal table. To get the critical values that go with your alpha. Then once you have gotten your critical values, you're going to determine your rejection regions and you're going to shade the rejection regions. Then you're going to turn your test statistic p-hat into a z-score by using this formula. So the z-score formula is going to be p-hat, the sample proportion, minus p, the hypothesized population proportion, divided by the square root of p times q over n, all under a square root. Then you're going to put your z on your graph and see whether your z-score falls in the rejection region. If z is in the rejection region, you are going to reject h0. If it's not, you're going to fail to reject h0. And then don't forget to interpret your decision in the context of the problem. So don't forget that you are supposed to label which hypothesis was your claim, and you're going to interpret your decision based on which hypothesis the claim was. So let's say that a researcher claims that less than 40% of US cell phone owners use their phone for most of their online browsing. So one quick thing about any proportions, even though they're usually given as percents, in any of these formulas, you do want these proportions all as decimals. So let's translate this claim into math. So the researcher claims that, this is a percentage less than 40%, 0.40. So they claim that the population proportion of US cell phone owners P is less than 0.4. Since this is a less than and not a less than or equal to, this is the alternate hypothesis. So the alternate hypothesis HA is your P is less than 0.40, and I'm just going to label that this is my claim. Then right away, let's get the other hypothesis. So the null hypothesis, the opposite of less than, is greater than or equal to. So the null hypothesis, P is greater than or equal to 0.40. So let's get the rest of our information. In a random sample of 100 adults, so that is our sample size N, 31% say that they use their phone for most of their online browsing. So since this 31% was in the same sentence as the random sample, this is going to be our sample proportion of successes p-hat. So p-hat is going to be 0.31. At alpha equals 0.01, is there enough evidence to support the researcher's claim? So in this scenario, there are only two outcomes. They either say yes, they use their phone for their browsing, or no, they do not. So there's only two outcomes, success and failure. Success is defined as yes, I use my phone for my browsing. Failure is no, I don't use my phone for my browsing. So the hypothesized proportion of success involves this 40% or 0.40. The z-score formula is going to involve Q, which is the population proportion of failures. So remember, to get Q, you do 1 minus P, so 1 minus 0.40 is 0.60 for your Q. So next thing we're going to do is we're going to determine our rejection regions based on the type of test we have and our alpha. So let's look at the symbol that is in the alternate hypothesis. The alternate hypothesis contains a less than symbol, so this is going to be a left tail test. Since this is a left tail test, your rejection region is going to look something like this. You're going to have just one critical value, negative z0, and the rejection region is going to be the area to the left. Now remember, that area to the left is going to go with your alpha. So since this is a left tail test, your inverse normal tables always deal with area to the left. You are going to just, in the inverse normal table, look up 0.01, gives you a critical value, negative z0, of negative 2.326. And since this is a left tail test, all you have to do is just look up alpha as is in the inverse standard normal table, and that will give you your critical value. So negative z0 is going to be negative 2.326. This isn't the best drawing, but again, I'm doing the best I can with this. All right, so now that we've got our critical value and our rejection regions, let's turn our p-hat into a z-score. So we're going to use this z-score formula over here. So we're going to have p-hat minus p divided by the square root of pq over n. So our z-score is going to be p-hat, which was that 0.31, minus the population proportion in the hypotheses, 0.40, divided by the square root of p, which is 0.4, times q, which we figured out was 0.6, divided by n, which was 100. Now, I would recommend putting parentheses around that subtraction in the numerator and parentheses around that fraction inside the square root in the denominator. You should get a z-score of approximately negative 1.84. So then we're going to put our z-score on our graph. So this is to the left of the mean, but not as far to the left of the mean as negative 2.3. So it's going to be, again, this is good enough. It's going to be right about there. It's not quite this far to the left. It's about right there. So z is not in a rejection region. So our initial decision is that we are going to fail to reject H naught. Now, H naught was not our claim. HA was our claim. Remember, the only way that you can support the alternate hypothesis is if you prove the null hypothesis wrong. If you reject the null hypothesis, you can support the alternate hypothesis. But we did not have enough evidence to reject the null hypothesis, so automatically there is not enough evidence to support the researcher's claim. So if you failed to reject H naught and your claim was HA, there is not enough evidence to support the researcher's claim that P is less than 0.40. All right, so for this next one, a researcher claims that 86% of college graduates say that their college degree has been a good investment. So this is a claim. Let's translate it into math. So this claim is clearly involving a percentage. So this is a claim about a population proportion. The researcher is claiming that the population proportion of college graduates who say their degree was worth it is 86%. So P, they are saying, is exactly equal to 0.86. Since this is an equal sign, this is the null hypothesis, because the null hypothesis always involves equality. So since this involves an equal sign, this is our null hypothesis. And I'm just going to label the null hypothesis as my claim. So then I'm going to get the alternate hypothesis. The opposite of equals is not equals. So the alternate hypothesis is P is not equal to 0.86. So now that we've got our claims, let's figure out the rest of the information. In a random sample of 1,000 graduates, so N is equal to 1,000, 845 say that their college degree has been a good investment. So we actually have to do a little bit of work to get P hat. Remember, success in this case was defined as, yes, my degree was a good investment. So they don't give us P as a proportion. We're going to have to figure out what P hat is. So out of those 1,000 graduates, 845 of them said that it was a good investment. So we're going to take the number that said, yes, it was a good investment, 845, divided by the total number of respondents, 1,000, to give us a p-hat of 0.845. So we had to do a little bit of work, but there is our p hat. So remember, if p hat is not expressly given, you just take the number of successes in the sample divided by the sample size, and that will give you your proportion of successes in your sample. All right, so at alpha equals 0.10, so alpha equals 0.10, is there enough evidence to reject the researcher's claim? All right, now one other thing that we need before we get very far is Q, which is the proportion of failures. Now, there's only two outcomes here. It's either the graduate said that yes, this was a good investment, or no, this was not a good investment. So if 86% said it was a good investment, if you do 1 minus P, so 1 minus 0.86, you will get the proportion of failures to be 0.14. So let's look up our critical values based on the type of test. Now, since the alternate hypothesis contains a not equal sign, this is a two-tailed test. What that means is that the area in the two tails put together is alpha. So there's going to be two tails. One tail here on the left, so that'll have a critical value negative, that'll have a critical value of negative Z naught. And then you're going to have one rejection region, one tail here on the right, and that will have a positive Z naught. Now, in a two-tailed test, both of these tails put together is alpha. So this 0.10 is the two tails put together. To find the area of one tail, you divide it by 2. So each tail has an area of 0.05. And remember, this is a normal distribution, which means these tails are the same, and which means that these two critical values are symmetric. So what you're going to do is in the inverse standard normal table, you're just going to look up 0.05, and that will give you your left critical value. So if you look up 0.05 in your inverse standard normal tables, you get a negative Z naught of negative 1.645. That will then mean that the positive critical value, positive Z naught, will be positive 1.645. So I'm just going to label those on my graph as best as I can with this crappy stylus. So that's negative 1.645. And this one is positive 1.645. All right, so now what we're going to do is we are going to turn our p hat into a z-score. So our z-scores for proportions are going to be p hat, which we got as 0.845, minus the p in the proportions, which is 0.86, divided by the square root of p, which is 0.86, times q, which is 0.14, all over the square root, all over n, so over 1,000, parentheses around the numerator, parentheses around that entire fraction in the square root. You should get a z-score of approximately negative 1.37. So now that you have your z-score, you are going to put your z-score on your graph. Now, this is a negative z-score, so this is clearly to the left. However, it's not quite as far to the left as negative 1.6. It's really close, though. But it's not quite as far over as negative 1.6, so z just falls short of the rejection region. So your initial decision is that you are going to fail to reject H naught. Now you need to interpret this in the context of the problem. So your claim was H naught. So there is not enough evidence to reject the claim. Oh God. You get the idea. There's not enough evidence to reject the researcher's claim. Because we failed to reject H naught and our claim was H naught, we do not have enough evidence to reject the claim. All right, so that is going to be it for hypothesis testing for proportions, and this is going to be the end of the hypothesis test that we are going to do in this class. So thank you all very much for watching. Your third exam is going to cover Chapter 6 and Chapter 7, so it's going to cover confidence intervals and hypothesis tests. So the next group of lectures videos we're going to do are going to be on Chapter 9, which is going to be something called linear regression, and we will get to that after the third exam. So thank you all very much for watching, and I will see you in the next one.